another video about algorithms, and in this short video I will talk about understanding the complexity of algorithms. When we look at algorithms and their complexity, we have to look in a table, and it's on the next slides, where you find the time complexity of different types of algorithms or different types of time complexities with some example. Like I told you before, time complexity is important to understand because we will evaluate the algorithms on their time complexity. And time complexity refers to the duration that it will take for an algorithm to complete some calculations. Now, we know that when the data increase, the time complexity also increases. And it's very important to identify the different types of time complexities that we can encounter and how they are ordered. We also spoke a little bit about space complexity, but we didn't talk about it in this course because it's out of scope here. Although space complexity is very important when we are looking at the application of algorithms. And space complexity refers basically to the fact that we have to have a certain amount of memory available in order to complete the algorithm. Now, the algorithm is in fact the basis to do those calculations, but in the course of algorithm, we will also see how these algorithms treat the data, if they need more space, if they reuse the space, or what are the ways that the algorithms are in fact dealing with space. Let's have a look at the different time complexity cases we can have. The first one is big theta of 1, which is a constant complexity independent of the data amount. We find it for a search in an ordered array. We have big theta log n, which is the logarithmic complexity, which we find in binary search algorithms. We have big theta of n, where we have linear complexity, and which is linear search algorithms. Then we have big theta n log n, where we have the linear arithmetic complexity, which we find in merge sort. And then we have big theta n to the power b, where we have the polynomial complexity. For example, for bubble sort, there we have n to the square, so b is then equal to 2. And then we find big theta b to the power n for b larger than 1, which we call the exponential complexity, and this relates to matrix chain multiplications. Then we finally have big theta n factorial. We call it factorial complexity, and this is typically found when we try to solve problems like the traveling salesman. Now, there is also a concept what we call tractability and P and NP problems. When we have a problem which we call it tractable, when we can resolve it using an algorithm with polynomial worst case complexity. Now, it means that we can expect to resolve this problem in what we call a reasonable time. Now, when problems do not comply with this condition, when they are not tractable, we call them intractable. And some algorithms or some problems can also be unsolvable. There may be problems, Alan Turing has proven some of them, they cannot be solved with the methods that we have. Now, there is also a very important concept when we look at algorithms, that we have P and NP problems. So P means polynomial, we can resolve them in a reasonable time. And then we have the non-deterministic problems, and these are in fact the problems, they cannot be resolved in polynomial time. And one of the elements that is used, or that is using the principle or the condition of NP is in fact the resolution of encryption problems. Now, there is still an open question about resolving NP problems, finding that they or a polynomial solution. Now, this is still out. People are looking for this. They're trying to prove that condition. Now, one of the consequences, if this can be resolved, it means that the actual status of encryption is in fact not usable anymore, because the encryption is typically related to an NP problem. It cannot be resolved in polynomial time, so it's not tractable. But when we can find the solution by solving the P-NP problems, then the encryption is in fact not, or is easier to crack than before, because then we can crack it in a reasonable time. The fact that encryption today is so interesting is because it is NP. There is no polynomial solution that can resolve an encryption problem. The thing about algorithms is now that we finished most of the parts that I want to complete or to discuss in this course of discrete mathematics. We will be looking further into discrete mathematics, where we will be considering number theory and cryptography. You're doing a great job. We're already finishing a nice part of the course. Still a lot of work to do, but I'm looking forward to seeing you in our next video. Thank you and bye-bye.